Welcome to my talk about low-power IoT communication security on the performance of DTLS and TLS 1.3. My name is Hannes, and this work was done together with Gabriele and Emanuel. Let me start with the motivation of why we looked into this topic. I think it's widely known that Internet of Things devices need communication security. You can read this in various government guidelines. Here are two examples from ECOSA and from NIST, recently published documents. And that by itself is not sufficient. We also have specifications that make use of TLS and mandate its use or use it in one way or the other. Here are three examples of recent specifications. On the right, the lightweight M2M specification in the latest version 1.2, which was published a few days ago, the FIDO IoT specification, which is a work in progress, and the ANIMA PRISCI specification from the IETF. But specifications themselves also are not sufficient. But luckily we have many deployments also using TLS to secure the communication of IoT devices, and here are some proprietary solutions that use TLS, Microsoft Azure, AWS, and the Google Cloud. But luckily there's also a lot of standardized sort of implementation or implementations of standards, in this case lightweight M2M, and I picked a couple of companies that use and implement the lightweight M2M specification all along with their TLS or DTLS specification. So that's a pretty good state we are in currently. Of course, as the popularity of TLS led to mass deployment in general on the web, but also on IoT devices, the number of attacks increased. And here's a nice chart from a presentation on Real World Crypto 2018, which shows the different attacks on a timeline. And while many of the attacks are addressing older crypto in using TLS, which the IETF has long deprecated, it still shows that there is a lot of investigation. So even if you have a protocol that doesn't have any attacks, that doesn't necessarily mean that there aren't any. But if a technology is very popular, more and more researchers are looking into it. And of course, they find some ways to attack it. So what was the IETF's response to this? It was a new version of TLS, of course, in addition to recommendations on how to configure earlier versions 1.2 correctly. So it's not, hope is not lost for 1.2. It's actually a perfectly fine protocol, which is obviously still in widespread use. And with the appropriate parameters and configuration settings, it's a fine protocol. But still, looking forward, going into this new effort, the IETF did, or as it always does, it developed a specification in public, and it was reviewed by a large community. I would even say by an extremely large community. If you look at the TLS mailing list, it was just, for years, it's just incredible amount of effort. The work was formally verified, and there were various interop tests, and we actually participated at some of them. And the new version led to performance improvements by reducing the number of round trips, and I'm going to talk about this a little bit later, and by omitting certain messages. So it got more lightweight in that sense. It also got improved on sort of new features added, and other things got simplified as part of this exercise. It was a kind of a redesign. So session resumption, for example, was harmonized, which functionality was previously spread out in different pieces, if you will, was merged and harmonized into a single pre-shared secret-based exchange. There's now an explicit version negotiation, and also the concept of post-handshake messages was introduced instead of using the renegotiation mechanism that was available previously. Also, I think quite important and probably the shiniest thing is the increased privacy and security protection, and which was influenced by work that came out of Snowden's revelations, and which were captured in this specific document. So when we talk about TLS on IoT devices, what do we actually mean by IoT devices? IoT is a very nebulous concept, and for some people it's just a mobile phone or the set-top box or a game console or whatever. But here we are talking about something different. This RFC 7228 talks about 3 classes of IoT devices, class 0, 1, and 2. Class 2 corresponds roughly to 50 kilobytes of data size, so RAM, and 250 kilobyte of code size. And that's roughly the area where we are talking about here. Class 1 would also be acceptable, but these classes unfortunately do not talk about what goes into that memory in terms of functionality. And if you look at an entire IoT device, including like the operating system and also firmware update mechanisms, device management solutions, etc., then it's better to actually have a little bit of headroom, because you need to keep multiple flash images for recovery, etc., etc. And as time moved on, so we have more powerful chips. So here's an example, a specific example, one that we also use in our test setup is an STM32F103. It's a 32-bit Cortex, ARM Cortex M3 processor microcontroller, which has pretty generous sort of data points. The flash is 512 kilobytes and the RAM is 64 kilobytes. That's a very good setup for any IoT deployments as far as our investigation concerns. So this is really more than enough. But it's something that you would find typical IoT devices today. On the right-hand side, you see the block diagram, which shows all sorts of peripherals on that microcontroller, on this system on chip. And you will see there are numerous protocols and numerous features, which is pretty exciting. And some of them, modern ones, also have crypto acceleration in there as well. So this is not uncommon anymore. It was less common a few years ago, specifically when some of the other IoT work in the IETF was started. So we are in a much better position now. So we want to run TLS and DTLS on those type of devices, which requires us to do some look at the way how we write code and how we use features. So how widely deployed are these microcontrollers? So like, are we talking about some exotic thing here, or is this something else? And here's some data published by ARM, recently presented to the Java Card Forum, which showed on how many processors, which include microcontrollers as well as larger processors, shipped in the last 30 years. And you see, for the first 100 billion chips, it took 26 years, and in the last 4 years, 100 billion more of those were shipped. While ARM doesn't provide detailed statistics about the types of processors that were sold, nor do other companies, you can get an idea that we are talking about a gigantic number here. And if you then add on processors from other companies, then you get a good sense of a development that is not, or type of technology that is not a rare occurrence. So we are talking about some real numbers here. So real stuff. Luckily for developers, there's also a lot of implementations. Here are a few that I found that I linked here. But many of those, if not for almost all of them, are focused on web and web applications. And so those are obviously written without any specific performance considerations in mind. They use languages which are typically not available on IoT devices. So there are much fewer stacks that even use the 1.2 functionality on the embedded side. And if you then look into the new recently published TLS 1.3 specification, there are even fewer. And then coming to DTLS 1.3, which is currently in the final stages of standardization, this is actually they are the first implementation we provided, public implementation. So what are our contributions in this paper? So first we developed the embedded TLS 1.3 implementation. Then out of this, we produced the DTLS 1.3 open source embedded applications. We did a comparison with 1.2 and 1.3, of course, in terms of features. And then we did our performance evaluation, focusing on different implementations and different hardware setups. And then we also provided our experience back to the standards activities to improve their specification. So let's have a brief look at how TLS and DTLS 1.3 works. I assume that most people are familiar, if not all, are familiar with the earlier version 1.2 because it's such a pervasively used protocol. So anyone working networking is likely to be familiar with that work. So here's the exchange in red. You can see when application data can be transmitted securely. And this is sort of the basic exchange with public key-based authentication. And you may recognize many of the names, the message names from earlier versions. What is distinct here or different to 1.2 is that many of the payloads have actually moved up front to earlier messages, to the client hello and server hello / encrypted extensions message to allow this reduction in messages. We look at this, the key share contains the Diffie-Hellman public key that is sent from the client to the server, because the public key variant always uses perfect forward secrecy based on Diffie-Hellman key exchange. And of course, the server needs to respond to that key share, this Diffie-Hellman exchange as well, with its own key share. And then you see servers and clients obviously demonstrating possession of the private key and the public key is part of the certificate that is exchanged in a separate message. So those, and we assume here mutual authentication, which is the common use of TLS in an IoT environment. If we look at a new feature that was introduced in 1.3 is called the zero RTT handshake, which allows transmission of the application data already in the first message. So you cannot really do better than that. And this is accomplished by using pre-shared secret-based authentication exchange, which is conveyed in the pre-shared key payload. What is also worthwhile to note here is that this exchange requires some replay protection at the application layer, so some additional API changes. But otherwise, this is a high-performance exchange, and the symmetric keys used here can be established using the full exchange shown previously. And here's the, sort of a variation of the zero RTT exchange based on also pre-shared secrets, but just without using this early data. So then the messages, the application data traffic is transmitted a little bit later, not with the first message, but with potentially with the server sending a response to the client, or after the first round trip. So pre-shared secret is, as the name indicates, it's computationally much less demanding. You can still see that there is an optional Diffie-Hellman key exchange in there, which of course provides its own provides benefits in terms of forward secrecy, but it's optional. So here you see the pre-shared key, and sort of this is a MAC-based calculation then, and this is sent forwards and backwards. What you can also see from the style of the way how the messages are wrapped is that messages are encrypted much earlier. So except for the client and the server hello, all the messages are encrypted. So what is specific to DTLS 1.3? We made a bold move to optimize and produce a variable length record header to provide optimization of the actual application data that's being sent. It's used already during the handshake, but where it really shines in terms of efficiency is once the connection is set up and application data is protected, because then the overhead from the record layer is minimalistic. On the right, you can see sort of the full-blown version with the optional connection ID, with a variable length sequence number and an optional length indication. The connection ID provides a new way to identify a DTLS packet, and it allows the connections to stay alive much longer. So it's a great performance improvement. We had to add a new handshake reliability mechanism because of reports from the earlier versions of DTLS, which were when used over unreliable networks, it didn't provide good performance characteristics under heavy loss. There's a privacy feature to encrypt the sequence numbers in this exchange, and the DDoS protection mechanism, which existed already in previous version of DTLS, was upgraded to use the TLS 1.3 cookie mechanism. So let's jump into the analysis on what we investigated. We looked into flash usage, RAM, which means heap and stack. We looked at the power consumption and energy used for those exchanges, and also we looked into the over-the-air overhead. We omitted the CPU investigation on how much time it takes to make these computations, because there is already an investigation in that area in the benchmarking group called Embassy, with under the title of Secure Mark TLS, and it's a synthetic benchmark for TLS exchange, and it answers the CPU related questions. So here's the setup. We used 3 different boards. We used a board from Nordic, the NRF 528040, which was mentioned in earlier presentations already. We use a custom board, they call the IoT Lab M3 node, with a Cortex M3 processor, the processor I had shown previously on my slide. And then finally, another development board based on Kyle. This uses another STM32, but this time it's a Cortex M4. And those are, and that's something to keep in mind, those are development boards where the features of the microcontroller are used almost to its maximum, where the different pins are exposed to different peripherals, and made it easy for developers to try out new functionality. So the more features they are offered, the more expensive the board is, but in general these boards are very inexpensive, but the plain microcontroller is ridiculously cheap. Software-wise, as mentioned, we wrote our own DTLS TLS stack, but we compared it in the performance against the Wolf SSL 1.3 stack, which is another embedded stack. Unfortunately, Wolf SSL doesn't have a DTLS 1.3 stack yet, so we could only focus on the 1.3 TLS comparison here. We used Riot as the middleware, which includes networking. We used 2 Riot nodes to communicate over a 6-LoWPAN and a co-op stack, and we integrated the different DTLS libraries for that purpose. We wrote an application that uses this combination, and we used ATLS, application layer TLS, to run the DTLS communication on top of it. Of course, there's no reason not to also use TLS underneath co-op, or DTLS underneath co-op, but in this specific case we wanted to also look into one of our more recent development on ATLS. We didn't use hardware crypto. This is something that is investigated, or the impact of hardware crypto is investigated in the Secure Mark TLS benchmark on the Embassy website. Clearly, using hardware crypto makes a huge difference, and I'm going to briefly mention this in a later slide. For our energy measurements, Nordic kindly offers a power profiling kit, which we use, that provides us with an relatively easy way to get the power measurements. if we look at the TLS stack, we have to keep in mind that a lot of the code base is actually based on the crypto. And this slide aims to show that. So if you look at a purely BSK-based variant, then you see that TLS stack itself, the TLS protocol, contributes 40% to the size. The rest is related to the crypto. Symmetric crypto, 42%, the HKDF, the new key derivation function, and the random number generator and its construct, the pseudo random number generator. Even more extreme is the situation once we use public key crypto, as it is the case with ECDSA, ECDHE, with the NIST curves. Here, the B256R1. You see that the TLS stack itself only has, or contributes only 22% of the overall code size. So if one uses hardware-based crypto and moves some of that crypto into the available silicon, or basically omits the software-based implementation, this is obviously a gigantic saving, clearly. So this is something to keep in mind. So whenever you optimize something, if you optimize for the wrong stuff, then obviously that's not going to get you too far, or it's maybe a wasted time. We've also earlier looked into the impact of crypto libraries on the overall performance, code base, RAM utilization, in general for resource consumption. And this was work done based on firmware updates. So we looked at a common cryptographic function needed there, which is elliptic curve digital signature. And we looked at different implementations. And here's sort of the summary of this. The paper is linked below. And fewer stars is better here. But what you see here is that there are trade-offs. So it's not possible to have an implementation that does everything great but has no side effects. So that's something to keep in mind. And here you see the differences, like in terms of flash usage between wolfSSL and Mbed TLS. And what is not shown here is sort of the details on the resistance against, for example, side channel attack mitigations, or in general, like how you could use that implementation for certain primitives. So this is something to keep in mind as you compare one protocol against the other one, because many of the protocols actually tied pretty strongly to an underlying crypto implementation, and swapping out one crypto implementation against the other one is like a significant rewrite of the entire work. So I wish it would be different, but that's what the developers face today. We also noticed that configuring an embedded security protocols or embedded crypto in general is difficult. So you need to, because of code size optimizations, you need to work with the C preprocessor directives, and you need to configure the right stuff. You need to understand how those directives relate to the features you want at the protocol level. And you, of course, you need to have a good understanding of the implications of setting or unsetting certain configuration options, as in terms of performance and also in terms of security. And so configuring two stacks that use different crypto and have different design goals in the same way to make a good comparison is extremely difficult. And that's something we spend a lot of time on. We reached out to developers and so on, so it's not easy. But let's come to the comparisons. So we looked at the flash size, which is of course important for developers of IoT devices. They want to make the code fit into the flash, needless to say, and leave headroom for another firmware updates. And so what we can see here is that if we compare 1.2 against 1.3, in this case, the table shows Mbed TLS on the Cortex M4 with the number of bytes, that we see about a 20% increase of code size. And that's in part, or to a large part, due to the new key derivation function that was introduced in TLS 1.3. So it's the HKDF construct and the special use of of it in TLS, which added to the code base. But that new construct made it easier to do the formal analysis and also made security better. So I think it's a good investment. When we look at the RAM utilization, and here's the table showing Mbed TLS and Wolf SSL, we can see that the numbers, without looking at the details, the numbers vary quite a bit. So like if you go from line to line, you see like the huge differences. And also sort of like the stack uses in general like smaller and of course constant almost. And we were wondering of why Mbed TLS has this huge stack size. And it turned out that this is due to a configuration of the AES algorithm because it can be configured to either be small in ROM or provide better performance, thereby using more RAM, in this case more stack usage. So you can change this and rebalance it if you want, but so once you decide for one setup, you also need to carry it through. But there are lots of ways to fine-tune it, fine-tuning possibilities that may not exist in other implementations. There's also a branch or version of the Mbed TLS, which is called bare metal, which lowers the RAM utilizations, which shows us that even if you have a specific protocol, if you make certain trade-offs, you can actually go to a much lower RAM utilization at the expense of more development efforts. Okay. If we look at the energy consumption or energy measurements we did, you can observe that in general there's lower or equal amount of energy consumption. So it's actually a pretty good indication of what has been done here. Despite the larger number of key derivation steps, it actually didn't make the difference. The fact that the message or some of the messages got omitted and the whole exchange optimized, that sort of made up for it. Clearly, what is noticeable is the huge difference between symmetric and asymmetric crypto, which you can, for example, see here. If you look at, let's say, the ECDSA Mbed TLS and compare this with the PSK version, like it's a gigantic difference, which also sort of hints to the use of the resumption mechanism and also the connection ID to actually stay with symmetric crypto as long as you can and only use asymmetric crypto when absolutely needed. We also noticed an interesting artifact which also tells us an important story on how to configure the stack. In the 1.2 implementation, we allow record backing, which the DTLS specification allows. So you copy multiple records, TLS messages together into one underlying UDP datagram and send it off, thereby omitting the headers of these different messages. And clearly that leads to a smaller payload size and fewer messages being sent around. And in 1.3, in our 1.3 implementation, we didn't make use of that feature yet. And so you see a significant increase in energy consumption compared to what we had previously. Still small compared to a public key-based variant, but those sort of details matter. And if configured incorrectly or if certain features are omitted, it actually shows shows up in the measurements. The bytes over the air transmitted, that's less exciting in some sense. There's a decrease for DTLS 1.3, also contributed by the variable length and optimized header that I had shown previously, a minor increase for DTLS 1.3. But the biggest contributor here is clearly the exchange of the certificates. So on certificate chain, we used a flat PKI hierarchy. So the certificates make a difference here. So speaking about certificates, there's clearly a couple of optimizations which we used with the DTLS, but many others we didn't. So we used the ticket-based resumption. As I explained earlier, we also implemented and used the connection ID, a very powerful feature which might require an investigation on its own regarding the performance. But then when we look at different ways to reduce the size of certificates, there are many different options from client certificate URLs all the way to new certificate formats, which we haven't utilized yet. But there's certainly a lot of potential. There are ways to reduce the RAM usage, and we use the maximum fragment length extension here. But there are also various other techniques, the trusted CA indication, the ability to reduce the number of tickets being sent, the size of extensions, and the most recent development is compact TLS, which compresses the TLS exchange and the DTLS exchange radically altogether. So that's something we will have to look into next. Some of those extensions are already further along in its development. Compact TLS is a more recent effort. Okay, let's finally talk about the next steps. So standardization work for IoT crypto is still in progress. There are different groups, and the ones relevant here are the IETF Lake and the TLS working group. So feel free to join those and follow along. We are planning to work on a prototype, or we are working on a prototype alongside the standardization work to see or to support the standards activities. We also want to evaluate various IoT extensions mentioned earlier and their performance implementation. We also noticed when we did the performance analysis, there is a lot of room for optimizations here. So we'll optimize things here and there in the code as we see more developers being interested in it. And yeah, help us to improve the IoT security by contributing to a stack like MPTLS, and the repository is linked here in the slide deck. And this is work done, or MPTLS is work done in the trustedfirmware.org consortium, and so they are happy to take contributions from everyone. And with that, I'll leave you, and I'm happy to receive questions. Thank you.